Imagine a telescope so powerful that it can see the first stars and galaxies that formed in the universe more than 13 billion years ago. The telescope would be able to look back in time by taking advantage of the fact that light travels at a finite speed. When we look at an object that is 65 million light-years away, we see it as it was 65 million years ago, because that's how long it took for its light to reach us. The farther away we look, the further back in time we see. The telescope on the Moon would be able to see objects that are so far away that their light has been traveling for almost the entire age of the universe, about 13.8 billion years. That means we could see them as they were when they first formed, shortly after the Big Bang. This would allow us to witness some of the most mysterious and important events in cosmic history, such as the end of the Dark Ages, when the first stars and galaxies lit up the universe, the formation of supermassive black holes and quasars, and the evolution of galaxies and their structures over billions of years. We could also test some of the fundamental theories of physics and cosmology, such as inflation, dark matter, dark energy, and gravity waves. The Moon-based telescope is still a concept, but it has been proposed as a potential project for NASA's Artemis program, which aims to return humans to the Moon by 2024 and establish a sustainable presence there. The telescope would require a lot of resources, coordination, and innovation, but it could also inspire a new generation of scientists and explorers who dream of seeing the dawn of the universe. In this video, we'll explore how this ambitious idea could revolutionize our understanding of the cosmos and our place in it. The Moon is an ideal location for a telescope because it has no atmosphere to distort or block the light from distant objects. It also has a dark side that is shielded from the Sun and the Earth's radio interference, making it perfect for observing the faint infrared signals from the early universe. The closest exoplanet that might support life is a super-Earth orbiting a red dwarf star called Wolf 1061, which is 14 light-years away. That means it would take light 14 years to travel from that planet to Earth, meaning they would see our Earth around 2009. James Webb Telescope can see objects over 13.6 billion light-years away, which means it can see what the universe looked like around 250 million years after the Big Bang. It can also see details as small as a US penny at a distance of about 25 miles, or a football at 550 kilometers away. If someone on another planet looked back on Earth 13.6 billion years ago, they would not see anything at all. That's because Earth did not exist yet. Would an alien life form have the incentive to travel that far? That would depend on the motivation and curiosity of the travelers. They can only make a judgment based on a snapshot from the past and wouldn't know that humans lived now on Earth. If they had warp capability, they would warp into a civilized Earth and not the gaseous cloud of dust they first viewed through their telescope. Another example would be if you were 66 million light-years away from Earth and had a powerful enough telescope, you would see Earth during the Cretaceous period. This is a form of time travel without participation, since you are observing the past without being able to interact with it or change it. Some people might argue that this is not really time travel, since you are not physically moving through time, but rather receiving delayed signals from distant sources. In this context, a human might say it depends on how you define time travel. This is more a window to the past that you can't affect, which is a fascinating concept. The light-years distance would always determine how far back in time you would be able to see. Your origin and perspective would influence how you interpret what you see. For example, if you came from a different planet or galaxy, you might have a different understanding of history and culture than someone from Earth, as you could only see the past. Now the interesting thing is to extrapolate this knowledge to technology that would make it possible to have a telescope to view such detail, To view 66 million years ago, at a detail of 1 meter at planetary ground level. This is the diameter of the telescope objective needed to view such detail. This is 2,270 times the distance from Earth to the Sun, or 2.7 times the diameter of our galaxy, and is an extremely large and impractical size for a telescope. As for whether this technology would be possible, I cannot say for sure. Maybe with some advanced engineering and physics, such a telescope could be built or simulated somehow. But with our current knowledge and technology, it would be impossible. Moore's law. The suggestion is to use the Moon as a platform for a giant telescope. This would have some advantages over Earth-based or orbiting telescopes, due to zero atmospheric interference, less gravity, and more stability. It would have many challenges, such as high costs, logistical difficulties, and environmental risks. Currently, though it's an impossible size for a telescope, without adding miniaturization with Moore's law. Using current miniaturization and past technological advances, let's look at how long would it take before we could miniaturize a time telescope to fit on the Moon. We can try to make a very rough guess based on some assumptions and simplifications. First, let's assume that the size of the telescope objective is proportional to the wavelength of the light it collects. This means that if we use shorter wavelengths, such as ultraviolet or X-rays, we can reduce the size of the telescope. This also means that we need to account for the absorption and scattering of these wavelengths by the interstellar medium and the Earth's atmosphere. Let's assume that we can somehow overcome these challenges with some advanced technology. Second, let's assume that the rate of miniaturization does follow Moore's law, which states that the number of transistors on a microchip doubles every 2 years. This implies that the size of a device decreases by half every 2 years. This is a very optimistic assumption since Moore's law is not a physical law and may not apply to all types of technology. Third, let's assume that we want to fit the telescope on the Moon in a reasonable size, such as 100 meters in diameter. The telescope would be made of a thin film of reflective material that would unfurl on the lunar surface, forming a dish. The film would be controlled by wires and motors that would adjust its shape and orientation to focus on different targets. This is still a very large telescope, but much smaller than the ones we calculated before. Now, let's do some calculations. To view 66 million years ago, at a detail of 1 meter at planetary ground level, we need a telescope with a diameter of 72 billion kilometers. If we use X-rays with a wavelength of 0.01 nanometers, instead of visible light, with a wavelength of 500 nanometers, we can reduce the diameter by a factor of 50 million. This gives us a diameter of 1.44 million kilometers. This is still too large to fit on the Moon. To fit the telescope on the Moon with a diameter of 100 meters, we need to reduce the size by another factor of 14,400. Using Moore's law, this means that we need to halve the size about 14 times. Since each halving takes 2 years, this means that we need 28 years to miniaturize the telescope. Therefore, my very rough guess is that it would take about 28 years to miniaturize such a time telescope to fit on the Moon, using current miniaturization and past technological advances. This is based on many assumptions and simplifications that may not be realistic or accurate. The actual time may be much longer or shorter depending on many factors and uncertainties. Realistically, the technology would be available no later than 2050, but the project could be built earlier with the technological changes being added modularly. The formula for the angular resolution of the final miniaturized Moon telescope is resolving power equals 11.25 seconds of arc/d, where d is the diameter of the objective expressed in centimeters. Since we are using X-rays instead of visible light, we need to adjust the wavelength accordingly. The wavelength of X-rays is about 0.01 nanometers, while the wavelength of visible light is about 500 nanometers. Therefore, we need to multiply the resolving power by a factor of 50 million. Resolving power is equal to 11.25 by 50 million seconds of arc/d. Resolving power equals 562,500,000 seconds of arc/d. To view 66 million years ago, at a detail of 1 meter at planetary ground level, we need an angular size of 1.56 times 10 to the power of -12 arcseconds. To resolve this angular size, we need to solve for d in the formula. D equals 562,500,000, 1.56 times 10 to the power of -12. D equals 3.61 times 10 to the power of 20 cm. D equals 100 meters. This is the diameter of the final miniaturized moon telescope that can view such detail. A project like this would give humanity unforeseen knowledge, and is within reach this century. Record the past in detail. Civilizations that once existed. The problem with how time and space work is all these views are echoes of the past, and we have no idea what the current situation of any planet would be. This would be fascinating and valuable for humanity. It would allow us to learn more about the history and evolution of the universe and its inhabitants. It would also raise many questions and challenges about the nature and ethics of observing the past. That we cannot know the current situation, we can use the past as a clue to infer some possible scenarios and outcomes for the present and the future. We can also use the past as a source of inspiration and wisdom for our civilization. Ideas like this are certainly not new. Watch the classic Star Trek episode, The City on the Edge of Tomorrow, and you can see the potential for such a powerful telescope, though it would always be a passive window to the past, unlike the active portal the crew of the Enterprise encountered. One further thought: if you're an alien, would you visit Earth from a great distance on the off chance of meeting other sentient life? Probably not, as the risk is too high. How do you navigate using star maps based on light sources from the past that may disappear during your journey? Going to any planet other than what's in your solar system would need a lot of luck and hope. My conclusion from this is that unless you have a warp drive, aliens would not take the risk of interplanetary travel outside their solar system. A time telescope, though, is such a wonderful idea for discovery. Let me know your thoughts.